We present a tree-structured shading decomposition, a pipeline to obtain a tree representation for object shadings. Analyzing the visual appearance of an image is the focus of intrinsic image decomposition. The goal is to factorize an input image into a shading layer and a reflectance layer. However, typical representations are highly limited and difficult to edit. In computer graphics, a powerful editable representation is the shade tree. This representation allows decomposing complex visual effects into basic elements such as albedo, highlight reflection, environment reflection, etc. Given its flexible editing capabilities, shade trees are often used in vector graphics to depict stylized materials. In this example, the shade tree is used to render the line drawing with a shiny red material. A shade tree has a binary tree structure, where the leaf nodes of the tree are all basic nodes that cannot be further decomposed. These include specular highlights, environment reflection, albedo, and diffuse shading. The internal nodes are formulated using a specified composition method that takes both child nodes as input, like the multiply and screen operation. By executing the tree in a bottom-up manner, we can produce complex layered visual effects. In this work, we propose a method to infer the shade tree from a single image. Given an input image of an object and its corresponding appearance, our model is able to decompose the appearance into a shade tree. The representation can then be reused to generate new shade trees, enabling images to be edited intuitively. As an example, let's consider the two trees shown here. We can combine and reuse subtrees in each representation to generate a new shading, which can then be executed and applied to a new object. This shading can then be rendered out to the final object image. It is also possible to directly edit some of the nodes. For example, we can edit these two nodes in the right tree, which can then be executed to generate a new shading. As a result, we can easily re-render the object appearance in the original image. We conduct extensive experiments to show the effectiveness of our proposed pipeline. In this example, we compare the decompositions of a realistic object between our method and two other baselines. Our method successfully gives a reasonable shade tree decomposition, while the LSTM and transformer gives similar structures but incorrect nodes. And the CNN cannot finish the decomposition because of its deterministic inference. Our model can also deal with cartoon-style objects. In this sample, our method effectively decomposes the given toon shading, while the LSTM and transformers struggle to find the correct nodes. And the CNN is not able to finish the decomposition. Here, we show a comparison of different methods on a sample that is not in the same domain as the training data. Our model can perform the decomposition even in this case, showing the generalizability of our proposed pipeline. Conversely, the other three methods fail to produce a good decomposition because of their poor robustness. We are able to obtain decompositions of in-the-wild results as well, as shown here. Moreover, we can recover the representations from the original vector shade trees paper. We can also first extract shading from vector graphics and then obtain decomposition of those appearances. Our method could also be applied to non-spherical geometry in real images by first using off-the-shelf tools to extract the shadings. Further ablation studies show that removing various components of our pipeline results in a decrease in the performance of the proposed method. Let's go over each stage of our pipeline more carefully. The first stage attempts to obtain the initial structure prediction for a given input using an amortized inference module. This step is performed in a top-down recursive manner, with an autoregressive module that recursively decomposes a parent node. Of this stage is a promising initial guess for the shade tree. There remain some nodes that are not decomposed successfully. Thus, these nodes have unknown substructures. To solve this issue, we pass the unsolved nodes to the second stage of our pipeline, where we search over all possible structures and find the optimal substructure. Finally, we combine the results from both stages and perform optimization on the entire tree parameters to obtain the final result. Let's look at the first stage of our pipeline in more detail. This module is recursively applied to each step of the tree decomposition. Given the parent node at some intermediate step, we first use a VQVAE encoder to obtain a latent representation of the node. This latent code is then passed into the first autoregressive module, which samples the latent code for the left child. The latent code for the left child is then fed into the decoder to produce a corresponding image representation. Similarly, the latent codes of both the left child and the parent are passed into a second autoregressive module to get the latent code of the right child, which is also decoded into an image. The parent node, left child, and right child are then fed into an operation prediction network. This predicts the type of operation performed to compose the two child nodes, such as the screen mode shown here. Finally, each of the predicted children is fed into a child type prediction network to check for further substructure decompositions. If the node is a leaf with no need to be further decomposed, it is passed into an optimizer to get its parameterized representation. Otherwise, it is recursively fed into the module for further decomposition. Here we go over the details for the second stage of searching for an optimal substructure. For each node that is not successfully decomposed in the first stage, we aim to find the optimal substructure to explain the shading in this stage. To accomplish this, we search over all possible tree structures. For each structure, we optimize the parameters for the leaf nodes and try to minimize the reconstruction error between the execution result of this tree and the input image. Afterwards, we calculate the reconstruction loss between the optimized result and the input and compare it among all candidates. We choose a structure with the smallest error as our final output. Thank you for watching. For more details, please refer to our paper.